Hey everyone, welcome to our quick unpack. Today we are going to be talking about efficiency in HVAC. We've got Mo Afshin here with us. We are going to be offering PDH credits today. So if you are looking forward to that, please email marketing@qpac.com. It is listed at the top of the screen. That way you'll reach out to me directly. I can get you those credits. Other than that, any questions, anything that you have, please feel free to put them in the chat. I will interrupt Mo and we will kind of make this a conversation between all of us. I know a lot of people are going to have questions, especially about all the topics that Mo's about to dive into. So I will quickly turn it over to Mo. Again, questions in the chat, email me at marketing@QPAC and we'll talk to you soon.
Thank you, Eddie. Thank you, everyone, for joining today. It is still morning in the West Coast, so good morning or good afternoon if you're in the East Coast or Central. I am one of the sales managers at Q-PAC, and I'll be speaking about efficiency in fans and fan systems today. I am a member of ASHRAE 5 Technical Committee 5.1, which is on the fans as well. And I work with our original equipment manufacturer partners. That's my role today at Q-PAC. As Eddie said, please go ahead and ask your questions. It'll make the presentation much better, and I'm sure a lot of people have a lot of comments, or if you are working or you've worked on an interesting project that is related to the topic today on efficiency, please share that with us. I know everybody would be interested to know. So today, it's going to be a very basic look at fan system efficiency. And first, we're going to talk about system and component efficiency and what we think a system is. Then we'll dive into the efficiency and why we need efficiency drivers of efficiency. We'll talk about the two metrics that a lot of people may have heard of or know about them, fan efficiency grade and fan energy index. So most of the bulk of our presentation today is going to be about those two metrics, how to calculate them, how to find them, and how to use them. And then I have just one slide about efficiency in general and what it is. As manufacturers, we get tunnel vision. We work a lot on the efficiency of our components, but then that component is going to go into a box and deal with other components and then go into a building and deal with a lot of other things. So what efficiency is very important. Let's move on. So what a lot of us mechanical engineers are familiar with, that's my background, is static efficiency. We care a lot about, a wheel, a device that goes into the airstream, moves, and then moves air. The feed is working, and I saw your question, Brandon. So thanks for checking. So that is the static efficiency of a fan. So that's what has been really what we were looking at really before, is the static efficiency. That's what we see on the schedule, that's what we see in the specs when we're designing a fan as a system. And that is what you see in a fan curve. So when you pick a point that is good on a fan curve, that is basically looking at the aerodynamic side of a fan. It is only the impeller part of the fan. Although when looking at a fan, you have a lot of other components that a lot of the time we don't look at. Now, when I first started, yeah, my slide is a little bit funny looking there, but when I first started designing fans, when I started at a custom manufacturer, how I was taught to design fans is to run my operating condition, run my CFM static, and find a good looking fan curve to see where the operating point is, not to be too close to the stall point, not to be too far off from the main part of the fan curve. Look at the static efficiency of that fan, find the brake horsepower, and then add about 10 to 15% to that brake horsepower and select a motor for that fan. So the only part that I always saw when designing a fan was the static efficiency. I never saw anything else. I never saw anything downstream of that air when I was selecting a fan for a system. And I always thought that, the most important part of that efficiency is just the aerodynamic efficiency of that fan. Now, looking at a fan system as a whole, you see that there are a lot of other components that come within efficiencies. So today we're going to look at, the codes, standards, the drivers of efficiency, how they evolved based on, just the aerodynamic side of a fan, going into a fan system that includes a lot of other components to actually move that fan impeller or that fan wheel. All right. Eddie, let me know if there are any issues with the slides or anything.
So far, no issues.
All right, perfect. Now, after defining that system efficiency, that is going to be including all parts, including the impeller, the motor, the bearings, the drive, and the belt, if there is a belt, versus that static efficiency that only is looking at the impeller, let's talk about the drivers of efficiency. Now, there are multiple reasons why we pick higher efficiency components. Of course, comes with better ROI. Of course, comes with lower energy usage in our buildings. But the main reason, it's an anecdotal thing for me, but the main reason I've seen people pick more efficient systems is because we have to. What forces us to pick more efficient systems are the building codes. The main basis of building codes that are issued by states or cities is ASHRAE 90.1. So ASHRAE 90.1 on the commercial buildings and on residential buildings, there are two issues of ASHRAE 90.1 and 90.2. For commercial buildings, it is ASHRAE 90.1. It is a minimum efficiency code. That means if you comply with 90.1, it doesn't mean that we've designed an efficient building. It actually means that we've designed a building that has minimum efficiency. So that is the definition of minimum efficiency code, which is ASHRAE 90.1. It goes through revisions every 3 years. Some of these revisions come with a lot of changes. So we're going to go through one of the changes that happened in 2019 that was important for fans. And then there are differences between states. So some states use 90.1 as a base and then go a lot more stringent. Some states use just different revisions of ASHRAE 90.1, and it may not be the most up-to-date one, maybe from 2013 or even 2007, which is the first 90.1 that came out. The first metric that was introduced by 90.1 was a metric that was introduced by AMCA in 2011. So that's the first time that ASHRAE and AMCA introduced a metric to look at the efficiency of fans when they go into design. And it was called Fan Efficiency Grade, or FEG. So in 2013, that was adopted by 90.1. So any state that follows ASHRAE 90.1 2013, between 2013 and 2019, they will need FEG when designing new construction. Now, what is FEG? FEG is a unique value that looks at the peak static efficiency of a fan. It only looks at the aerodynamic efficiency, so it doesn't look at anything upstream of that fan wheel. It only looks at the fan wheel in the air, and it only looks at the peak efficiency. What I like to say about FEG is that it shows how good a fan wheel, an impeller, can be when it's designed perfect, when it's designed at perfect operating conditions. And I have an example here of how FEG can be, just by looking at FEG, can be misleading. So it's only, first of all, it only looks at the aerodynamic side of the fan system, and it only looks at your peak operating efficiency. So that's a fan wheel that's one of the fanciest fan wheels down there. It's I can't even say it. It's a biomimetic fan blade. It was designed, if you look at those little corrugations on the fan blades, this is an airfoil based centrifugal fan, and those corrugations are based on fins of a whale. So I don't know, 200 engineers sat down and figured out how to make it work, and make it 3% more efficient. They came up with this really fancy wheel, and it has an FEG of 85. The maximum FEG you can have is 90. So that fan, if designed properly, is going to actually have 85% efficiency, static efficiency. So it's a very fancy, very efficient wheel. But if you use this fan in a situation where your CFM is 6,000 CFM, so it's a fairly small wheel, at half an inch of static, the efficiency that you're going to get is less than 40%. So it's really important to know that FEG is only showing you how good that fan can be. It doesn't really tell you how good that fan is in your application. And in order for ASHRAE 90.1, in order to mitigate that problem, they have another clause in the FEG, and they are going to say that if you're designing your fan has to be within 15% of your peak efficiency. So this is what a lot of people just look at the FEG. They don't look where their fan is actually operating in a system, and you're not going to comply with 90.1 in that case. So you have to be within 15%. So if your peak efficiency is 80%, you have to be, not below 65% with that fan when you're designing at your operating point. See, there's a question. Is there any advantages to Q-PAC? Fan array for compliance to local 97. New York City in section during the Q-PAC. I am not very familiar with the 97 and 179D tag. Oh yeah, I am a little bit. Yeah. I don't think they look exactly at these metrics, but I really need to. If you have any more info on what actually the 97, the New York City 97 is, then I might be able to help you with that. But otherwise, I have to look at 97 New York City because I'm not familiar with that law, Michael. But I know that 179D, that is for government buildings. And in order to comply with that, I'm pretty sure that we have had projects in the past that have complied with this, but it is for only government buildings and for specific criteria. There's a big criteria to actually follow for that one.
Maybe I can provide a little context for you, Mo, just for local law 97 really quickly so that we can answer that. Yeah, so it says that under the law, most buildings over 25,000 square feet will be required to meet new energy efficiency and greenhouse gas emissions limits by 2024. It says that the largest buildings will need to, the goal is to reduce the emissions produced by the city's largest buildings by 40% by 2030 and 80% by 2050.
Yeah, so that would be holistically looking at buildings. So definitely using more efficient fans is going to help you get there. But I don't think it is just the fans. You're looking at the whole building efficiency, reducing by 40 and 80%. And that is on your gas. Is the fan more efficient than? Yes. But again, you definitely have to look at yes, ECM fans, depending on the application, are going to be more efficient. But for that to comply with that one, you'll have to look at the whole building. becomes a little bit tricky when you're talking about, decarbonization and you're talking about reducing carbon footprint. Fans are electric. So even AC motor fans, even like the fans from 100 years ago, they use electric motors. So you don't have a carbon footprint if your electricity is clean. Then you don't. I don't know if New York City's electricity is clean or not, but your carbon footprint by going to a lower, they're both electric equipment. So it becomes tricky when you want to reduce your carbon footprint. You're going to reduce your energy consumption, which becomes very important when all these cities are going electric, and the load on your power supply is going to become really high. Then reducing your power consumption becomes really important. Although you're replacing a less efficient electric motor with a very efficient electric motor. So they both might be, carbon neutral because they both are using electricity.
Right. And maybe you could speak to it that just in the context of most buildings that they're running at partial load. So I think that ECM fans are traditionally more efficient at partial load, which is usually how buildings are running them, as far as I understand.
For sure. Yeah. We'll talk about that in a couple of slides. So yeah.
Great. Thanks, Michael.
Um, all right, let's move on. So in 2019, just because of those two main issues with fan efficiency grades, just because they were not looking at, fans as a system, they were only looking at the aerodynamics efficiency of fans, and FEG was only looking at the peak efficiency of a fan, another metric was introduced by AMCA. In 2019, that was adopted by ASHRAE 90.1, and it's called Fan Energy Index. So now Fan Energy Index is looking at the efficiency of a fan system at the operating point. So it is a calculated number, and it looks at the efficiency of that whole fan system from the drive, from your VFD to air, or wire to air efficiency of that fan, and it's looking at that at your operating conditions. So you can actually run it at operating condition. So it's solving the two problems that FEG had before. It is also a very simple metric to look at. So I have a graph, if you can see it, it's a tiny graph at the right side. So you can see that, FEG, that peak efficiency of that fan that was selected is at 75%. But when you're operating it, you're actually operating at 56, 55%. So that shows a difference between, your FEI in this situation is going to be, uh, below that 55% because it's looking at static efficiency, but it's so much lower than that peak, that FEG. When somebody asks me what the difference is between these two, a really simple way of saying it is that FEG tells you how good a fan wheel is, how good a fan wheel can be if it was designed perfectly. And FEI tells you how good a fan system is at your operating condition. So that is the difference between these two definitions. Even for a lot of the cities and states that use FEG that are based on ASHRAE 90.1 prior to 2019 revision, I recommend just, a lot of the time it's very simple to find the FEI of these fans. So you can ask, the manufacturer to get the FEI, look at that metric, and it tells you an apples to apples comparison. You can compare it, one fan system with another, and see which one has a higher FEI, so has better efficiency. Now, how we can find these values. For FEG, there is all of these fans have to be certified by AMCA. So these are metrics that are only available for AMCA certified fans, first of all. And then if it is an AMCA certified fan, there is a library online that you can go and find the FEG of that specific fan. So I have the link up there. We'll share these slides so you can just Google it and find that at the AMCA website, and you can find the FEG of the fans that you're using. Again, this is a unique number per fan wheel and shows the peak efficiency of that fan wheel. Or if you couldn't find that in that list, you can actually measure the FEG of a fan. So it depends on that formula over there depends on the total static and CFM and brake horsepower of the fan. So you can calculate that and then use the graph on the right, that is the graph by AMCO 205, and find the fan efficiency grade of that particular fan that you're working with. And for Q-PAC fans specific, it's extremely simple. All of the fans that we use have an FEG of 80. So that's the list over there based on the fan models. All of our fans have fan efficiency grade of 80. We have a question from John. The FEI is only analyzed at design condition. Many fan systems variable load will slow down. Fan efficiency generally decreases. That's very correct. So that again goes back to the shortcomings of our metrics today. So even with FEI that has solved a lot of problems with efficiency, now we can only look at efficiency at our design condition. Now, a lot of the times, you know, when we're designing, as engineers, we like to first of all over design because nobody wants a building to not be designed for the full load. So we always design for 110, 120% capacity, and that building is always going to operate at, you know, maybe 50% capacity. So it's going to be occupancy of 50%. That system is always going to run at, you know, 50 to 70% of the load. So FEI, when looking at FEI, they're going to look at the FEI at peak operating point. That's where a lot of the motors, a lot of the AC motors are going to operate at their highest efficiency. So they're going to design based on highest FEI. Now, when they go to part load, a lot of these fans, a lot of these motors, AC motors with VFDs, are going to operate at reduced efficiency, and that's going to reduce the total efficiency. So that's another problem with FEI, but it's a much better metric than FEG, but there's still a lot to go when you're looking at your design. Question from Barry.
Yeah, maybe you can repeat the question as they come through and as you read them, just because there are some people watching on LinkedIn who don't get access to this chat. So if you could just repeat Barry's question and then answer it. Thanks.
So John Weikert's question was again what we talked about, that FEI only looks at design conditions. It doesn't look at part load design. So a lot of the fan systems that are designed for variable air volume are going to operate at part load. So that FEI that was used at design, at the beginning of the design, may not actually be correct when you're operating your fan system at part load. And that is correct. We have a question from Barry. Are your fans a fixed size? And can the fan do 60,000 CFM at 4 inches of total static pressure? Also, if they are molded fans, does the fire marshal have a smoke spread issue if caught on fire? So our fans are fixed size. That is correct. And how we go into larger CFMs or larger static pressures, we use multiple fans. We use multiple fans to create a fan array, and that way we can increase the capacity of that fan, that particular fan. So yes, we can do 60,000. We have done 200 to 300,000 CFM fans before. That comes as a combination of fans to get to that higher CFM. We do use fans that have composite wheels, and those composite wheels are all smoke tested per UL for smoke spread. So they have all passed fire and smoke spread tests by UL. They have fire retardants and smoke retardants, so they're not gonna spread smoke and fire. All right, now let's move on to FEI. So fan energy index, again, there is a formula to calculate fan energy index. How it is designed to work is to look at the fan input power of your actual fan running at your design condition, comparing that to a reference fan by AMCA. So you will need basically the wire to air input power of your fan system. In our case, it would be very simple because all of our fans are rated based on wire to air input power. So we exactly know how much power goes into our fan systems, even at design. And then comparing that to a reference fan by AMCA. And that reference fan is actually not a super efficient fan. That is a belt drive fan with a mediocre motor. So you're comparing it to that, and you want to be more efficient than that fan system. And this is how your equation looks like. So first of all, a big portion of the efficiency of a fan is that aerodynamic, that static efficiency. So that H value is your static efficiency. Then you're looking at, if there's a belt, how inefficient that belt is. Then you'll look at the motor inefficiencies, and then you'll look at, controls, electronics, and drive inefficiencies. So all of those come into effect to find the FEI. Just looking at FEI, it's very simple to see how you can improve on your fan. You can go with a more efficient fan wheel, or you can go with the direct drive system instead of belt drive system, or you can use better motors. That is where, John's question came, that motor efficiency. So motors are most efficient when they're at their peak load. So when you're running that motor if it is an AC motor, when you're running it at, its design peak load, that's going to be the most efficient that motor is. Now, if you reduce the load, if you're going to 50% speed on that motor to reduce your CFM to 50%, then that motor is going to be less efficient. So that is important to know, and you can calculate FEI at any operating point. So you can actually calculate FEI at 50%, CFM. That's not a problem. You can ask your manufacturers to tell you, what the FEI is going to be at that 50%. And I do recommend people do it. When you're designing at 100% and it's for a variable air volume system, just ask the manufacturer to give you FEI at 50% operating point. And then you can compare it and see how much efficiency you're losing when you go down to that 50%. And finally, going back to 90.1 and where we need to be. So for those cities and states that still use FEG, your fans have to have an FEG of 67 or more. And again, that FEG by itself really doesn't mean anything. So you'll also have to be within 15 percentage point of that peak efficiency. So if your peak efficiency, your FEG is 80, then your fan design cannot be less efficient than 65%. So that is the important part to keep in mind. And a lot of the times that's hard to check. That 15 percentage point. So a lot of the times, a lot of systems are not really designed based on that 15% off of your FEG. So that isn't going to comply. And it may not be as efficient of a system. That is the repeat of what we talked about. And FEI requirement. So for FEI, you have to be a 1.0. A 1.0 FEI means that your fan system operates the same as your reference fan. And above that, so that number, any higher that gets, your fan system is more efficient. A lot of our systems at 1.0, again, is not a super efficient system. A lot of our fan arrays and our fans, you're operating at 1.3 to 1.5. So we can be easily 50% more efficient than the reference fan. For fan arrays, the requirement is even lower than 1, so it's 0.95. That would be for fan arrays. Now, how to get that FEI? A lot of the manufacturers do give it to you, so you'll see it on the submittals. With Q-PAC, right now we do not show it in our submittals. You have to work on that to get our software updated. We do have a calculator that we can share with anyone who wants to get it and find the FEI number. I really like the FEI value because it's, first of all, it's a unit-less number. It's a value that tells you how efficient your fan system is going to be. So you can compare that between two fans and see which one is more efficient. If you're getting, from two manufacturers, two different fans, you're using two types of different fans, and you want to compare them and see which one is more efficient than the other one, you can just look at the FEI and you will see how they operate compared to each other. And as we talked, FEI is still not a perfect metric. And when we talk about, is a fan system, we are still looking at a fan that is tested in a perfect condition. It's tested in an AMCA certified lab. Everything is perfect. Everything is good. But that fan is going to go into a building. It's going to operate, there's going to be bends, there's going to be elbows, there's going to be a coil in front of it, and then there's going to be lengthy ducts that are going to go across the whole building, right? So when we are talking about FEI, this is a graph that shows it really well. That we are on paper, we are designing our system to be on that A point, although when that fan goes into the building, that fan goes into an air handling unit and then goes into the building, because of the system effect, because of the cabinet effect, because this fan is going to be contained inside of a box, and then there's going to be coils and there's going to be ducts, that fan is going to operate in less efficiency. So it is important to keep in mind that these are, again, not going to be exactly the efficiency that you're going to see in the building. There's going to be a slight reduction between what you see as an FEI, what you see in the building. And, a lot of the efficiencies depend on how a fan system is controlled. We never know how they're controlling this fan system, how they're using that VAV, how they're using their speed control, how that is well operating, how you have connected your occupancy to your fan so that you deliver, exactly the amount of air that you need. I find it personally that operating, even behavior of the occupants, are a lot more important than designing a system that is more efficient. Like, we've come a long way in designing systems that are really efficient, but then I think right now a good emphasis should go on how we operate these really efficient systems so we can get more efficiency out of them. And that is all I have for today. If you guys have any questions, please let me know, or comments.
Yeah, we'll hang out for a couple seconds or a couple minutes.
Yes.
Thank you guys for attending today. Again, if you're looking for those PDH credits, please email me at marketing@qpac.com. And there will be a short follow-up survey that I'll send after this, just so that everyone who is in attendance today can give us any feedback, any topics that they enjoyed, didn't enjoy, things we can talk about in the future. We're always wanting to bring you all content that you're really excited about.
So there's a question regarding the system efficiency that we have on our submittals. So the system efficiency is basically the wire-to-air efficiency of a fan system. So if you look at this is a traditional fan. It comes with all different components. The fans that we use are EC motors, and all of these components are inside of that motor. So when you see an efficiency of 60%, that is wire to air. So that means 60% of the kilowatt that goes into the Q-PAC fan actually goes into air. The email address, Eddie. Somebody is asking for that.
Yeah, so the email address, Bill, is listed, or it's just shown right at the top of the screen, right next to our logo. It says marketing at q-pac.com. So at q-pac.com. And I can put it in the chat as well if that's easier for you. For asking.
Awesome. Yeah, thank you very much, everyone, for your time.
And if you think of a question later, find us on LinkedIn, send us an email at marketing@Q-PAC, like I said, and we'll absolutely get back to you. I think Barry had a statement or a question there for you, Mo.
Some projects require USA made or assembled. Well, our products are USA assembled, I would say. And a lot of our components are USA built. I don't know if, I'm not sure if there's like a percentage of all our components have to be USA made for the product to be. And we might have someone on, I saw a comment from Matt. So Matt might know it if he's still on the line, if he can comment on that. But I'm honestly not 100% sure.
Right. Yeah, our arrays are built and assembled in St. Augustine, Florida. But like Mo said, some of our components, I'm unsure of what the ratio is.
But it's definitely, yes, assembled. Everything is assembled in Florida.
Perfect. We'll give it maybe another minute and just see if we have any questions that pop up. Again, reach out to marketing@Q-PAC. LinkedIn, we love connecting with people, having conversations there. And any other events, any other avenues, always happy to be the people answering questions.
And if you require that PDH credit, please, again, email that marketing email and we'll get back to you.
Absolutely. So I'll be sending up a follow-up survey. We'll stay in touch and advertise for our next quick unpack, which will be about this same time near the end of November. We will dodge Thanksgiving. We promise we won't try to rope you into FEG and FEI talks on Thanksgiving. But other than that, yeah, reach out at marketing@Q-PAC. We'll see you on LinkedIn and we'll see you at our next event. Thanks for attending, everybody. And this will also be placed on YouTube right after the event. So if you missed anything or have any questions, it will be on there and you can post comments and we'll get back to you as soon as possible. Thanks, everyone.
Thank you so much. Thanks, Eddie.